do right now today is we're going to prepare for the Let's Talk Science engineering challenge. Okay, so the engineering challenge is make a marshmallow tower. That's for kindergarten to grade 6. So that's what they have. This is not our project. Our project is for grade 6 to 8, which is you have to make a video. Okay, and it starts from here. Learn more. Okay, so from here, as you can see, this is an engineering challenge, and plants are precious resources of ours. They provide us with oxygen and are used as food. They have many other purposes, such as being used for pollination by bees. Therefore, we must try our hardest to protect these precious resources. Unfortunately, sometimes natural disaster can cause great harm to these resources. You have just arrived at the home of a farmer desperately needing your help. The farmer has a greenhouse full of crops and that's being grown. Recently, the farmer learned there were tsunamis nearby, which luckily didn't cause any damage. However, the farmer fears a powerful one is coming soon and will destroy the precious crops in the greenhouse. Your challenge is to design and build a structure using the listed materials that can keep the greenhouse, for example, any small object from getting wet. Water poured in a container. View the video to start.
Tsunami-proof structure engineering challenge. Tsunamis are a series of massive waves generated when water is rapidly displaced vertically. Any geological event, such as an earthquake or underwater volcanic eruption, can produce a tsunami. If tsunamis are powerful enough, they can destroy agricultural lands and greenhouses, which hold essential crops that is necessary for us. Sometimes, tsunamis are so powerful that they can have lasting negative impacts even months later. Challenge. Your challenge is to design and build a structure using the provided materials that can keep a greenhouse from getting wet. Materials: 1 small greenhouse, a cake pan, a measuring cup, and water. For the structure: craft sticks, small ball of plasticine, 1 piece of paper, drinking straws, and tape. Rules. The greenhouse will be at one end of the pan and the water will be poured at the opposite end. The water must be poured quickly so as to simulate a tsunami. The pan must be sitting horizontally on a flat surface. No part of the greenhouse can get wet. Success! You have created a structure that keeps your greenhouse dry. Pushing the envelope. Can your structure be made with fewer materials? Can your structure greater volume of water? Would the structure protecting your greenhouse be practical in real life?
Okay, this is the challenge. Okay, and then you can make a video on 2 minutes and upload it. We also have Let's Talk Science challenge, which is the lessons. Yes, so we'll go to the math one, and the first one is combinatorics. It's combinatorics. Okay, in combinatorics, mathematics is a very basic sense describes relationship between numbers and other measurable quantities. It's called the language of science. A strong understanding of mathematics is essential in order to develop a deep understanding of science. There are many different branches in mathematics, each with many unique and fascinating aspects. In this backgrounder, you will explore ways in which we use mathematics to understand how things can be arranged. This is known as combinatorics. We hope This gets you to think of mathematics in a whole new light. Combinatorics is a branch of mathematics that counts the number of ways we can arrange certain objects into sets and subsets. Multiplication principle. The multiplication principle is all about counting the different ways that things can be combined without worrying about the order things are in. Here is a typical question. A daily has 5 kinds of soup and 4 different sandwiches. How many different lunches can you have at the daily consisting of 1 soup and 1 sandwich? Okay, so daily has 5 kinds of soup and 4 different sandwiches. How many different lunches can you have at the daily consisting of 1 soup and 1 sandwich? The multiplication principle says if in one event, such as choosing a type of soup, X is the number of ways, and second events such as choosing a type of sandwich can occur in y numbers of ways, then the 2 events can occur together in x and y number of ways. In other words, we just multiply the possibilities. So to answer the question above, you have 5 choices of soup, x is equal to 5, and 4 choices of sandwich, y is equal to 4. So there are 5x times 4, y 5 times 4 is 20 possible lunch combinations consisting of 1 soup and 1 sandwich. Okay, if there are more than 2 events, we can still use the multiplication principle. For example, suppose the daily has 7 different drinks. How many different lunch combinations can you have with 1 soup, 1 sandwich, and 1 drink? The answer is at the end of the background. Okay, so what we're going to do right now is, okay, make it bigger. So how many did we have sandwiches and soup? So we had, okay, we had 4. Okay, I'm going to change the color and make it purple. Okay, so we have 4 sandwiches, 4 sandwiches, 5 soups, and 7 different drinks. So what is 4 times 5? 20, and 20 times 7 is 140. So what you have to do is multiply 4 soups, 5 sandwiches into 7 different drinks.
I don't have to do this because my friends are going to tell the answers, and I don't.
How many different lunch combinations can we make?
25.
4 times 5 times 7.
140.
140. Come. So we'll do another one. Okay, next. Here's another example. Suppose you have a lock that like the ones found on suitcases or used on some bicycle chains. It has a tumbler with 3 numbers. Lock with 3 digits numbers to unlock. Each of these 3 spinning dials has the numbers 0 through 9. How many different 3-digit numbers can we make using such a lock?
A million.
No, so I'll show you. Look, the first dial or even has 10 possibilities from 0 to 9. The second one has another 10 possibilities 0 to 9, and the third again has 10 possibilities from 0 to 9. So it's 10 times 10 times 10. 10 times 10 times 10. देखो तो 10 times 10 times 10 is 1000 different possible combinations, which is another way of saying 1000 different 3-digit numbers, which makes it tough for thieves to come up with the correct 3-digit number using only trial and error. Okay, you get it? So I'm going to show you. So how was it? It was 10 possibilities from 0 to 9, then 10 possibilities of second row, and 10 possibilities of third, and 10 times 10 times 10 is 1000. So there are 1000 possibilities. Question number 2. How many different license plates can you make if the first 3 positions have letters of the alphabet and the second 3 positions have numbers? Note 0 and Q are not included, are not used. The answer is at the end of the background. So A, B, C, D. How many A, B, C, Ds? 23 letters? Yes? So there are 23 letters. And how many numbers? From 1 to?
3.
No, it could be up till 9 they can use. So how many possibilities?
9.
23 times?
9.
1, 2, 3, 10 possibilities, sorry. So there are going to be 10 possibilities. Okay, let's see. So, sorry, we didn't want to save this, but anyways, we go down and see. So there are 23 possibilities of the alphabets, and O and Q remove, we would have 23. Y is equal 23 and Z is equal 23. Because they have to be 3 different letters, right? It's only just not one letter. So it's in number place, there are 3 letters, so 23 times 23 times 23. And it's 12,167. And 0 to 9, there are 10 possibilities. 10 times 10 times 10 is 1,000. So 1,000 times 12167 is 12167, 3 zeros. So there's 12 million possibilities. Do you get it, Aisha? You get A? So that's question number 2. So there are different possibilities. So look over here. So if you see A, in this row, there are 23 possibilities. In this row, there are 23 possibilities, A to Z. And in this, it said leaving, these are letters. And how many numbers here? 0 to 9, 10, then 10, and then 10. So you multiply, look, 23 times 23 times 23, right? And then 10 times 10 times 10. So this will 23 times 23 times 23. And then 10 times 10 times 10, 10 is 1,000. And then you multiply all these 3 and you will get so many possibilities. And you may never thought about that. Okay, next. Here's another example. Suppose about Abdul, Bianca, Cho, Dave wake up team of students in the Let's Talk Science channel. There are 4 questions. And each student must answer only one question. How many different ways if they could answer this question? As one possibility, they might go in order. So Abdul will answer question number 1, Blanca question number 2, and so. As another possibility, Cho might go first, then Blanca, etc. Listing all the possibilities could quickly become boring. Here's another quick way to figure out the question number 1. There are 4 possible children who can answer, and then one team decides who will go first. That person cannot go again. This means there are 3 students left to answer the question. There will be 2 students left to answer the question, and then last remaining. Okay? And the last, using the multiplication principle, 4 times 3 times 2 times 1 is 24 ways the student can answer the question. The first student can answer 4. The second will answer only 3 because 1 has already been answered. The third will answer 2, and then the last one 1. So the answer is 24. But wait, there's a pattern here. For instance, what if you were seen on planning what you were going to wear for school for the upcoming week? You have 5 favorite shirts. How many different ways could you lay out your shirts so that you wore for Monday a different one, Tuesday and a third for Wednesday, and so on the Friday? Using the multiplication principle, that's 5 times 4 times 3 times 2 times 1. 120 ways to lay out your favorite shirt for the week, and you thought you had nothing to wear. Okay? Now that you've got the idea, there's a little mathematical notation. Products look like this. 9 times 8 times 7.
Don't read all of it. You used to explain to me. Why are you reading this whole thing?
So you can understand.
Before you just used to just tell me the important stuff. Now you're reading it because of your video.
Are called factorials. These multiplying 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. They are called factorials. Instead of writing this, you can write 9 and the factorial sign. which means that the same thing takes place until space of the, and takes up less space on the page. It's also easier to say 9 factorials than to say 9 times 8 times 7. So in your example with Abdul, Blanca, and Cho and Dave, there are four factorials. 4 factorial possibilities in our last example with 5 shirts. So there are 5 factorials, 102 possibilities. Okay, we've done question number 2. We've done question number 1 and 2. Remember the alphabets? How many alphabets? There could be 12 million. And that's it. You get it? Okay. So there were 3 things. One was about the soup and the sandwich and the drink. There were 140 possibilities, 4 times 5 times 7. The second question was about the number plate. Okay. And there were 23 possibilities on X place and Y place and Z place. 23 times 23 times 23. And in the numbers, well, it was 0 to 9. There were 10 possibilities and 3 different places. So there was 10 times 10 times 10. 10, so it's 1,000. So it's 12,167,000. So that was the different possibilities. So there was a number plate about the lock. Do you remember the lock? There are 3 different places. So it's 10 times 10 times 10. How many possibilities for the lock combinations? How many combinations for the lock?
140.
Lock?
1,000.
Why is it 1,000?
Plus 10 times 10 times 10.
Yes, so it's 10 times 10 times 10 because in the row there's 3 rows. 1, 2, 3. So from here 0 to 9, which is 10. Here 0 to 9, which is 10, and 0. So the lock has 1,000 different possibilities. Okay. And then the last one was about factorials. And factorials means, so you don't have to do 9 times 8 times 7 times 6. You do 9 factorials. If you want to 5 times 4, 5 times 3, 5 times 2, you don't do that. You write 5 factorials. You get it? A, do you get it? Okay, next chapter. That was combinatorics. What was it? Combinatorics.
I don't want to do it. I don't want to say.
Combinatorics. What's the name of the chapter? What's the name of the chapter?
I don't want you to teach me like this.
What's the name of the chapter? Combinatorics. Second is about probability. Probability is introduction. Mathematics in very basic sense, we've done that. Relationship between the number and the other measurable quantity is called the language of science. A strong understanding of mathematics is essential in order to develop a deep understanding of science. Okay, there are many different branches in mathematics, each with many unique and fascinating aspects. In this backgrounder, you will explore ways in which we use mathematics to help us in the predict what happens. This is known as the probability. We hope this gets you in thinking of mathematics in a whole new light. Probability. Take a coin and flip it. Which side would you expect to land facing up? If the coin is fair, hasn't been rigged to a land specific side, you would probably say there's an equal chance of being head and tails, right? We use this phrase statement called probability. The probability of the coin landing head side and up and one is 2 is half. It can only be 2 possible choices, either head or tail, 50% chances, right? The possibility of landing a tail side is also 1 and 2. Note that if the sum of the possibility of all possible outcome is 1, the outcome of adding 1 is a fundamental property of probability. So 1 out of 2 choices, 1 out of 2 choices becomes 2 out of 2, or 0.5 plus 0.5. A question you might ask is, how do you know that these probabilities are correct? One way is to flip the coin lots of times, record the results each time, and then infer the possibilities from the results. Suppose you flip the coin 10 times to obtain the results. Head, tail, head, head, tail, 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 head, tail, tail, where T stands for tail and head for the toe, for the tail and H for the head. So it's 4 out of 10 and 6 out of 10. So it's very close to 5. Do you see it? A? Look. So it's 4 out of 10 were head and 6 out of 10 were tails. So both are close to 0.5. These values are close to the expected probability. Yes?
Yes.
Of getting a tail. 6 out of 10 is 0.6. So it's 0.4, 0.6 is close to 0.5. These values are close to expected value of 0.5, but they don't exactly agree. Why is this? Because you will only get the expected possibilities. You flip the coin an extremely large number of times. The more times you test, the closer to the expected probability you will get. You can try this with your class. It's interesting to consider questions that involve combining probabilities. This means that we use combinatorics and probability together. For example, suppose we flip the coin twice and ask for the probability. It's 1 upon 2. Okay, question. Let's go to the question now. For this, we can see that out of the 4 possible outcomes, only one leads to 2 successive tails, so the probability is 1/4. Question. A farmer breeds a white cow and a black cow. The calves, baby cow, have an equal chance of being either all black or all white, black and white faces, or white with black faces. Assume there are 4 possibilities. The answers at the back. What is the probability that a calf will be all black?
1 and 2.
No, 1 upon 4. 1 out of 4 possibility. What is the probability that 3 calves in a row will be of white? 3 out of 4 possibilities, yes? This is the answer, look. Where is the answer? And of the backgrounder. Okay, that's question number 2. Where's the answer? There it is, look. So question number 1, a farmer breeds a white cow. There is 1 in 4 chances of a calf to be all black. What's the probability that the three calves in a row will be all white? There's 1 in 4 chances of a calf to be all white. To have 3 in a row, that would be multiples of chances of each white. 1 upon 4 times 1 upon 4 times 1 upon 4. 3 chances, 1 upon 64. Look at this. So it's 1 upon 4 times 1 upon 4 and then again 1 upon 4. So 3 in a row is 1 upon 64 chances, or 0.016. 1.6% chance that they'll be all 3 in a row. Do you get it? Okay. We just have question number 2 to do and then we're done. Given the number of students in your class, what is the probability of 2 people in your class to have the same birthday? Do you have 2 people in your class have the same birthday?
No.
Okay, so how will you do that? So how many days there are? There are 365 days. So one student will have 1 out of 365 days, right? The second student will have 1 out of 364 days because 1 day has been taken. And then 1 divided by 364 out of 365, 0.9%. How many 3 students? As above, the first person can have any birthday and the probability second person is 364 divided by 365, and the third child will have. So look what you have to do. The first possibility is 364 out of 365. The second possibility is 363 divided by 365. That's the third one. That's the probability that all of these 3 students have a common birthday is 365 divided by 365 for the first student, 364 divided by 365 for the second student, and 363 divided by 365 for the third student. So we have 0.99. And if we subtract this from 1 whole, we get 0.82%, not even 1% chance. Do you get it? So that's done. So this is about all probability. We'll go to the third chapter. And the third chapter is about the third is encryption. So we did probability. How much was the probability? You have to do 1 out of how many times? 1 out of 4 or 1 out of 2? Third one. Encryption.
Sleep and every time you wake up,
Sit up, sit up. The third topic is encryption. As at the heart of any domain of science is testing of a theory. This can only be done when companies can be made in language of all scientific understand. This language is language is mathematics. Mathematics.
Nobody watching.
Mathematics enables groups of scientists who don't necessarily speak the same of language to work as a common problem and talk in a way that they can all understand. There are many different branches in mathematics, each with many unique and fascinating aspects. In this backgrounder, you will explore ways in which you can use mathematics to keep our data safe. This is known as encryption. How to keep your data safe. We hope this gets you and think of mathematics in a whole new light. We hope this gets you to think of mathematics in a whole new light and encryption. Whether you are a secret agent or student buying stuff over the internet, it's important to keep your information secret while you are transmitting it. For example, if you wanted to send a message about a surprise birthday party to a friend by email, it would be good to rewrite in a secret way, the only way your friend understands and your friend understands. Encryption is the term of creating secret messages. Decryption is the term for reading secret messages. Encryption and decryptions have been vitally important during wartime. For example, World War II, encryption and decryption centers were set up across many countries. One such center was Bletchley Park in England. Their cryptologists worked hard to decrypt messages from the countries they were fighting. A famous German cryptography machine created during World War II was called the Enigma Machine. Enigma Machine used a keyboard, a set of rotating disks, and electric circuit to create the secret codes. The electrical pathway from each letter on the keyboard to the output letter was charged often, so it was a tough code to break. Eventually, information about the machines and the hard work of allied cryptologists enabled the Allies to read the German coded message. This ability to find out that the Germans were up to without their knowledge helped the Allies win the war. Okay, an engine machine is used 1943. And substitution code. The Enigma machine worked by substituting one letter with another. This is called a substitution code. A substitution code is a code in which each letter in a word gets replaced by a different letter or symbol. For example, if you wanted to send your bank account hot dog to a friend in a secure way, you could use substitution code and rewrite it as this before sending it to your friend. Your friend could only be able to decode this message if he or she knows how you are substituting the letters. Given the example above, hot dog is coded as this. Would your friend need to know in order to break the code known as the encryption key? The answer is at the bottom of the background. Okay, so what we're going to do is another way to do a substitution code is to replace each letter of the method with the letter that is located a fixed distance from the letter in the alphabet. For example, a word danger becomes DJQ HIGO if you use the correspondence letter located 3 positions further along in the alphabet. This kind of encryption is called the Caesar shift cipher because Julius Caesar used it in the ancient Rome in relaying his messages. So we can make an example for over here. For example, now I want to make a code, say it's called cat. Okay, that's the secret word. So I'm going to send it and say you have to write 1 letter ahead. Okay, I'm going to write, so to decode it, you have to go 1 letter back. So what I'm going to be sending you is, instead of cat, ABC, I'm going to do D. AB, okay, the word is cat, right? So CD, instead of C, I'm going to give you D. A, I'm going to give you B, and T, STU. So I'm going to be sending you this word. So when you decode it, and I say, okay, you have to go 1 letter back. So you would decode D to be C, and B to be A, and U to be T, and you would know the secret word is cat. Okay, it's very, very interesting. So what I'm going to ask you, student, is to make a decode, and I'm going to decode it. So you're going to write a code, and I'm going to decode it, and I'm going to find out which one is it. So can you please write it? You want I can change the color? No? Okay. G J S F. Okay. Okay, so what is the key?
1 space forward. 1 space forward.
1 space for I have to do 1. Yours is already 1 space
In
forward.
the alphabet.
Okay, so yours is 1 space forward. So in order to decode, decrypt, I need to go 1 back, right?
No, front. In the alphabet.
I have to go 1 step. So you did it 1 step back.
No, front.
If you did front, then to decode, I have to go back then.
Yeah.
Okay, so this word over here is 1 letter ahead. It's encrypted. So it's encrypted to 1 letter ahead. And in order to, what happened here? Okay. I have to do this again because there was a problem. Okay, so what was the word? Okay, so this is the code word been sent to me. Is it correct?
Yeah.
Okay, so I'm going to change the color, and I'm going to, okay, so this is, again, this is coming, okay, this is what has been sent to me. So it has been encrypted to 1 letter ahead. Okay, and in order to encrypt it, I'm going to go decrypt. In decrypt, I have to go 1 letter before. Okay, it's been 1 letter ahead. So A B C D. Okay, A B C D E F G. So 1 letter before, it means it's F. this letter is F. Then A, B, C, D, E, F, I, J. It's I because here is J. Then J, A, B, C, D, E, F, G, H, I, J, K, L, M, N, R, Q, R. R. Okay. R comes first before S. So this letter is R. And A, B, C, D, E, E. E. Okay. Because E comes before F. So this was encrypted to one letter ahead. And to decrypt, I had to go one letter behind and I got the word fire. Is it the correct word? Yes?
Yes.
Good job. Okay. So this is all about. And this method, he did 3 letters ahead and 3 letters. It becomes more complicated. And it's called Caesar shift cipher because Julius Caesar used it in ancient Rome in relaying his messages. Question number 2. Create a Caesar shift cipher for the troops who are approaching and get a friend to solve it by giving him or her your encrypted key. A potential answer is at the end of the backgrounder. So basically you did with one word, the same you will do for the whole sentence. In the hot dog example, if someone intercepted the message, that person would have to figure out what substitution code you were using. For example, which letter does C stand for? The person might have to try all the possible combinations before finding what that makes sense. However, there are some tricks that could make the job easier. A clever interceptor could use clues like the number of times a symbol appears in the secret message. Since the letter E is the most common letter in the English language, the most common symbol in the secret message probably stands for E. Figuring out a method that way is called frequency analysis. The trouble with frequency analysis is that it only works when the message is long. So how can you prevent someone from using frequency analysis to decode your message, your secret message? One possible solution is to use different substitution codes for different parts of your message. For example, in the first sentence of the message, E could be coded to 96. And the second sentence, E could be coded to a star. If you change codes often enough, as the German did with the Enigma machine, it will be very difficult to find the pattern. So they send you the key separately. Okay, encryption keys. The information that only you and the person reading your code know is called the encryption key of the code. Encryption key. This is because it allows you to unlock a secret. For example, in a substitution code, the key is the substitution pattern you agree on with your friend. One simple type of encryption using key is called Symmetric Key Encryption. In this method, a key is used to encrypt the message and the same key is used to decrypt the message. The simplicity of this type of encryption is a drawback of this method. So you can see from the picture, it's a plain text encryption, and then there's a key. It's called cipher text and decryption, and hello there is the plain text. Symmetrical key, graphic text version. The original message is in plain text, and then encrypted with the symmetric key, which converts it into ciphertext. Ciphertext is decrypted with the symmetric key. Now the message can be used as plain text. A more tricky method is public key encryption. In this method, 2 different ways are used. One key is encrypt the message and a different key to decrypt the message. The key used to encrypt the message is called the public key. The key used to decrypt the message is called the private key in figure 7. These keys are mathematically linked in such a way that it's virtually impossible to guess the private key with the public one. Public key is a safer and preferable method for encryption than symmetric key because only the intended reader knows the private key. So you don't make the key private, you make it if it's public and private. Public key encryption. Okay? And this is ciphertext and then decrypt hello there. Plain text, hello there. So of course private key will be more secret, will be more because only the intended key reader knows the is more preferable, is a safer and preferable method. The original message is a plain text, is encrypted with a public key and converted to cipher text. The cipher text is decrypted using a private key. Now the message can be written as plain text. Compression code. A type of code studied by the cryptologist. Cryptologists are the ones who study the cryptology, is the compression code. Compression codes are ways to rewrite information using fewer characters so that it takes less space to store on a computer. Compression codes also help to transmit things more quickly over the internet. Take the following example. Welcome to New Brunswick. We could probably remove some of the characters in this message and still be able to read it. For example, if all the vowels in the message, okay, we can still read it. We can get a shorter message whose meaning is still fairly clear. This message only needs 2/3 of the original space to store on a computer. So removing all of the vowels in the English message is a simple kind of compression code. Other kinds of compression codes have been developed from other kinds of data. For example, JPEG is a method of compressing images. JPEG is an acronym for Joint Photographic Experts Group. What does JPEG stand for? Joint Photographic Expert Group. Morse code. The Morse code is a code that allows us to transmit text electrically. It was first demonstrated by Samuel Morse, its inventor, in 1844. He used it with his electric telegraph machine to transmit information over telegraph lines, which are wires for transmitting electrical signals. International Morse code is a modern variation of Morse's original code. In it, each letter of the alphabet is encoded at a different pattern of dots and dashes. Common letters are represented by short sequences. For example, a single dot stands for E. Less common letters are represented for long sequences. For example, dash, dash, dot, dash stands for Q. International Morse code. Do you see this? International. The length of a dot is 1 unit. A dash is 3 units. The space between the parts of the same letter is 1 unit. A space between letters is 3 units, and the space between words is 7 units. So these are the codes for the letters. Okay, if you want to make something, for example, you want to write a name, say you want to write cat. So what will you do? You will write okay, so if you want to write cat, what would you do? How to do that? So what you had to do over here is you have to make C dash dot dash dot and then A dot dash, and then for T you would have done dash. That would be cat. So you get the idea? Okay. Okay. The International Morse code source, there's one way of making the transmission as short as possible, since the short sequences will be used a lot and the long sequences only rarely. Therefore, the Morse code is a kind of compression code. Look at this. We're almost done. Question number 4 is really long. We did this one way of making transmission. Okay, decode the word in International Morse code. Okay, the answer is at the end of the backgrounder. Have you ever seen a fax machine short of facsimile machine? How are you going to decode this? 4 dots. What's the 4 dots? Do you have it here? 1, 2, 3, 4, 5 dots. Where are 4 dots? How are you going to decode this?
H H H L L O. Hello.
It's hello, but there are only 3 letters. 1, 2, 3.
1, 2, 3, 4, 5.
So what's the word?
Hello.
Hello. Okay, let's check the answer. H-E-L, 2 times L and O. Therefore, the word is hello. Good job. So you know how to decode. And let's go to the last one. Can you do this? Encode the rest of the picture above in both regular coding 0s and 1 and run length coding. Run length coding, line 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So maybe the question is over here. So let's say 0 represents a white square and 1 represents a black square. And to send the first lines of the picture in figure 10, we would send a message saying 0, 0, 0, 0. 0 ones, which is 21 character long. Let's say each character takes 1 second to transmit. The description of the first line of the picture would take 21 seconds to transmit. But there's a shorter way of transmitting a description of this line of the picture. Since the picture sent by fax machine often contains alternating long blocks of either white or black pixels, we can send a description of these blocks. We only need to send a message having how many pixels are contained in each block. This is called run length coding, and the picture above we could encode the first 3 lines 858, which takes only 3 characters. Assume that you always start with white. Okay. Encode the rest of the picture above in both regular coding 0s and 1. Run length codings and answers at the back of the pen card. Okay, just let's do 1. Can you do 1? Can you do this? Can you read this message?
No.
Okay, so just let's do 1. Okay, line 1. Can you read this? 696. Line 1, line 2. I think this is a line 2, right? Is this the one? One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5, 6, 7, 8. 8 and 8, 5, and 8. Is that correct? Okay, they don't have line 2, they have line 2. Okay, let's see what line 2 has. Do you know how to do this?
No.
1, 2, 3, 4, 5, 6. And then there's 1, 2, 3, 4, 5, 6, 7, 8. 9. 1, 2, 3, 4, 5, 6. So it's 6, 9, and 6. Yes, 6, 9, and 6. Look how I did this. Look. 6, 9, and 6. So 1, 2. So you look at this picture. You just have to count the numbers. Look, 1, 2, 3, 4, 5, 6. 6 white, so it's 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. and then 1, 2, 3, 4, 5, 6. So this line number 2, it says 6, 9, and 6. And if you check the answer is 696. So we can just do it from here. Look, line number 3. 1, 2, 3, 4, 4 zeros, 4, 1, 2, 3, 3, then 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, and then 1, 2, 3, 4. So you just have to count how many zeros, how many ones, how many zeros, how many ones, and how many zeros. So the answer is 4, 3, 7, 3, 4. Can you do the third one?
No.
Look, 3 zeros, 2 ones, 11 zeros, 2 ones, and 3 zeros. So this is how you do it up till 11. So this chapter is done.